All right, let's talk about the invisible language that powers, well, pretty much everything. We're diving into the world of signals and systems. I mean, just think about it for a second. The sound of my voice reaching you right now, the Wi-Fi signal beaming through your room, that picture on your screen, it's all just information, right? It's traveling in waves as signals. But the world is a super noisy, chaotic place. So how in the world do we build technology that can actually understand and control all of that? How do you pick out the one important message from all that static? Okay, so to even start answering that, we've got to be on the same page. Let's get down to basics. What even is a signal? At its heart, a signal is just a function. It's something that represents a physical thing we care about, usually over time. Think about the vibration of a guitar string or the voltage jumping around in a wire. Heck, it could even be how the brightness of one little pixel on your screen changes. That's the signal. It's the message itself, the raw info we're trying to grab. And signals basically come in two main flavors. You've got your analog signals. They're continuous, kind of like a smooth ramp. The real world is analog. Think of a dimmer switch, right? It goes from dark to bright in this perfectly smooth way. Then you have digital signals. These are more like stairs. They're discrete. They take that smooth reality and chop it up into a sequence of specific, separate values, kind of like a light switch that's just on or off. Okay, so if the signal is the message, well, you need something to actually do something with that message, right? And that, my friends, brings us to the second main character in our story, the system. So what's a system? It's basically any machine that processes a message. It's an interconnection of parts that performs some task on a signal. It takes an input signal, works some magic on it, and gives you a new output signal. Could be super simple, like an amplifier that just makes a quiet guitar sound lighter. Or it could be incredibly complex, like a radio tuner that has to find one specific station out of thousands broadcasting at the same time. It's the processor, the machine that does the work. Now, here's a really cool question. How do you figure out what a system is going to do? I mean, you can't test every single possible signal in the universe, right? Well, there's a genius shortcut. You give this system one single super sharp tap. We call it a unit impulse. And then you just listen. The way the system responds to that one little tap, how it rings out, is called its impulse response. And get this, that one response tells you everything you need to know about the system. It's literally its unique fingerprint. So the most obvious way to look at all this stuff is just watching it happen over time, right? We call this the time domain. We see a signal go in and we see what comes out. Seems straightforward, but predicting exactly what's going to come out, well, that's where things can get a little tricky. So to predict the output, you need to use this mathematical operation called convolution. Basically, you take your input signal and you take the system's fingerprint, that impulse response we talked about, and you kind of mix them together. But mixing here involves some pretty intense math. It works for sure, but it can be seriously messy and complicated. It's like trying to bake a cake using calculus. And this is where the story takes a brilliant turn. For a long, long time, this was just how it was done. Hard math. But then some very smart people started to wonder, what if there's a better way? A smarter way to see the signal? What if we're making the math hard on ourselves because we're just looking at it all wrong? And that was it. They were looking at it wrong. The big idea was to completely change perspective, to stop looking at a signal as this one complex thing changing over time, and instead to see it through a totally new lens, a new perspective called the frequency domain. The magic wand for this is something called the Fourier transform, and the best way to think about it is like a prism. You know how a prism takes a single beam of white light, which looks kind of boring and complex, and splits it into a beautiful, simple rainbow? The Fourier transform does the exact same thing for signals. It takes a messy, complex signal and breaks it down into all of its simple ingredients. A perfect recipe of all the pure frequencies that were added together to make it. And this is the punchline. This is the whole reason we do this. Remember that super hard, messy math, convolution that we had to do back in the time domain? Well, in the frequency domain, it becomes simple multiplication. Yeah, that's it. You just multiply. You take the frequency recipe of your input, you multiply it by the frequency recipe of the system, and boom, you have the recipe for the output. It turns crazy hard math into easy math. And that right there, that idea, it changed absolutely everything. And what's so cool is that this isn't just some neat trick for old school analog stuff. Nope, this fundamental idea of switching your perspective to make a hard problem easy is completely universal. It's just as powerful in our modern digital world. So it doesn't matter if you're working with those smooth, continuous analog signals or the choppy, discrete digital ones. The toolkit is basically the same. Sure, the names change a little bit. You might hear about a DTFT instead of a Fourier transform, or things like the Laplace or Z transform, but the game plan is exactly the same. You transform the problem into this easier world, you solve it with simple math, and then you transform the answer back. It's the same genius move every time. Now, I know this can sound kinda abstract, right? Just a bunch of clever math. But I cannot overstate this. This one idea, this shift in perspective from time to frequency, is one of the foundational pillars of our entire modern world. It's not an exaggeration to say that without it, our technology would look completely different. Why? Because once you can see that frequency recipe, you're not just a spectator anymore. You can become a chef. You can go in and edit that recipe. You can say, I want a little more of this frequency, a little less of that one, and let's just get rid of this other one completely. You can shape and control the signal with incredible precision. You're in charge now. And once you start looking for it, you see this idea everywhere. It's how an audio engineer gets rid of that annoying hiss from a recording. They just find the hiss frequency and cut it out. It's how we make MP3s. We literally just look at the frequency recipe of a song and throw away all the parts our ears can't hear anyway. It's how 5G and Wi-Fi can all be on at the same time without interfering with each other. They're all using different frequency recipes. It's how an MRI scanner can build a detailed picture of your insides using radio waves. And yeah, it's even the magic behind your noise-canceling headphones. They're listening to the world, figuring out its noise recipe, and then creating a perfect anti-noise recipe to cancel it out. It's amazing. So in the end, it all comes back to that one simple, powerful shift in perspective. By learning how to decode the hidden recipe inside every signal, we've given ourselves the ability to control and shape our world, from sound and light to communication and medicine, in ways that would have seemed like pure science fiction not that long ago. And that really makes you wonder, doesn't it? Now that we can decode all these signals, what will we build next?